Let's do problem number 31 on page 466 in chapter 16. Let's see. Let's read the problem from the book. It says here, it says, an electron is released from rest in a uniform electric field and accelerates to the north at a rate of 115 meters per second squared. What are the magnitude and direction of the electric field? So here I've set the problem up. Here's our electron. It's accelerating at 115 meters per second squared due north, and it has an initial velocity of 0, and we're trying to find the magnitude and direction of the electric field. So let's solve. So let me draw like a little free body diagram of this electron. It's accelerating to the north, which means that the electric field has to point to the south. And that's because, so here's our uniform electric field. It has to look like this. Now why? Well, because the electric field, by definition, is the force on our object divided by the charge on our object. Okay. Now, but the charge on our object is negative. Hey, listen up. Put the phones down. The direction of the electric field is what the electric field does to a positive charge. So what's it going to do to a negative charge? It's going to push it in the opposite direction. So if it's pushing this electron to the north, the electric field, because this is an electron, because it's negative, has to be pointed in the opposite direction, south. Does that make sense? Okay. So now let's figure out what the magnitude of this is. Well, what is the force on this? Well, we know what the charge is, but the force, well, if I draw a free body diagram of this, there's just one force on it, and that's the electric force. And this so this is also the net force, and the net force is equal to the mass times the acceleration on the object. So this is going to be equal to ma over q, at least the magnitude of it. And hey, I was looking at some of your work. So a lot of you had an equation, but it's nice to like how did you get that equation? From the this is the definition of electric field. That's a basic equation, and you can say, hey, this electric force is the net force on the electron, and so therefore it's equal to ma. So I'd like to see some steps shown. I think I gave a lot of you 6 out of 6 anyway if you didn't show that. But on the AP test, it'd be a good idea to really be explicit about every step. So now we can plug in our values. You have to look up the mass of an electron. It is on the equation list that I gave you. But I wrote it down here. It's 9.11 times 10 to the negative 31 kilograms. And the acceleration is 115 meters per second squared. And the charge on electron is 1.6 times 10 to the negative 19 coulombs. Now it is negative, but we've already accounted for the fact that it's a negative charge because we say that the field is pointed south, even though the electron is accelerating north. So you don't need to put the negative in. You've already accounted for it by stating that the electric field is pointed south. So, plugging in our numbers, we get 9.11 times 10 to the negative 31 times 115. And then I'm going to divide that by 1.6 times 10 to the negative 19. And I get a very weak field, 6.55 times 10 to the negative 10. Now you need to have units in there. And some of you left the units off. Ugh. Now, look, if you're confused about units, just put the fundamental units of kilogram meters per second squared per coulomb. Okay? But look, this is MA. MA is a force, and a force is measured in newtons. A newton is a kilogram meter per second squared. Yeah. And then the charge on here is in coulombs. Now to make this here, we have to say that it's pointed to the south. Now, some of you put a negative here, and it is a negative charge, and therefore you put a negative here, and then you said south. But that's redundant. If you're going to, this is the magnitude. Magnitudes aren't, well, you can technically have a negative magnitude. Actually, a negative magnitude with the direction of south implies that it's actually pointed north. But we don't do that in here. Don't ever do that. If it says magnitude of direction, just keep the magnitude positive. Just drop that negative. We've already accounted for the fact that the electron is negative. So this is our answer right there. Oh, almost screen. Oops. You got to tell me as soon as I'm off screen. Please let me know. Because I was off screen quite a while there. But I'm not going to redo it now. Any questions? That is